morning. I'm Marco Pradelli, and the title of my research project is Innovative Techniques and Methodologies for Embedded System Safety and Liveness. My tutor is Professor Luca Pazzi. So this is an outline of my presentation. I will start by presenting the research area and the motivation that originated my project. I will present both the traditional approach in the model of embedded systems, and then the Statecharts formalism, which I contributed to develop. Then I will present the 2 case studies and the other project which I worked on. So, embedded system safety is our main topics today because they are very present in our today life. And the open issues are how to build to ensure safety for embedded application, and in particular, how to build robust controllers for safety critical application. My research field is related to model-based engineering that its aim is to build a model of the system representing the system behavior instead of directly writing code by hand. This allows to achieve some advantages that are the model validation of a graphical representation of a behavior. And the code is, the software code is automatically generated in order to avoid the coding mistakes. The main topics of my field is the behavior representation. The traditional approaches deal with an implicit representation of the behavior that required to be emerged from an assemblage of components. And my project instead deals with an explicit representation of the behavior. This is necessary today because embedded system complexity constantly increases, and in order to be effective at validating and verifying the behavior, we need an explicit representation of it. So the traditional formalism traditional adopted for the system modeling is the Statecharts formalism. It's a well-known formalism. It is, for example, implemented in many tools like Stateflow, and it allows to deal with a graphical representation of the behavior, and many tools are effective in generating safe code for many embedded applications with several degrees of safety and optimization. The system verification in Statecharts is performed by a set of tools named model checking, but this formalism has some weaknesses. First of all, is the communication. We have a problem with communication because, as you can see from the picture, the 4 models of different components are strictly connected by the communication behavior. So it is difficult for a large system to extract one component and to reuse it as is in other projects, because some piece of communication is forced to carry the model of the component. So reusability is not easy to achieve with Statecharts. Statecharts instead tries to address the communication and reusability problem by adopting a hierarchical approach. In Statecharts, components are hosted into an assemblage of components that are not allowed to directly interact with direct message passing or value exchange. The communication must be performed through the whole section that hosts an explicit representation of the behavior that is required from the assemblage of components. In this way, the communication is refined into a more rigid paradigm, and the component behavior is explicitly represented in this section. This allows us to enclose the behavior into a diagram and to augment the modularity of the components and therefore of the system. Finally, in the whole section, the state semantics is restricted by constraints that I will present later. The semantics of part of the chart is computable in the sense that it is possible to perform the verification of the model at the design phase. This is possible because of the explicit representation and because each state is constrained by, this is a simple example, and so we formally know the set of the configuration that the assembly is able to reach while a given state is active. Starting from known semantics of each state, we can compute the transition pre- and post-conditions, and to verify, for example, if a transition precondition is allowed by the state constraint, so the transition will be feasible, and if the post-condition is compatible with the state constraint. Thanks to this construct, we are able to perform a validation in the design phase. Another concept that is at the basis of the verification procedure is the exit zone concept. An exit zone can be seen as a boundary configuration set inside the state semantics that is directly connected to an external configuration, for example, AZ1, by means of a non-controllable transition that is present in one of the components of the assembly. This means that once the system will be executed, when the controller will be installed and executed, this configuration represents a violation of the state constraint. So we need to provide, to cover the exit zone from the point of view of the verification. That means to provide a transition in the whole section, therefore in the controller, that is able to react to this configuration, to this violation of the constraint. So, by means of the exit zone coverage and the transition validation, we should be able to ensure that the system will always be able to react to every event coming from the real world, and that no deadlock are present because each transition is feasible and unfeasible transitions are shown to the user during the modeling phase. Now let's move to another important aspect of embedded system, that is fault tolerance and fault management. We missed the fault term. So a fault can be managed at different levels because a simple fault in a component at a lower level, it can propagate through the whole system. So we need to provide a means that allows us to both identify faults and to manage them in order to be effective in fault tolerance and to prevent system deadlocks, for example, system deadlocks. So we can perform the identification of the fault at the component level, and then if the fault is related only to the component behavior, the fault is contained. Otherwise, the fault is propagated through the layers of the system. An example for that allows us to recognize, to identify faults, is this pattern for the modeling of sensor actuators. This pattern applies to physically connected sensor and actuators because we need to consider an actuator to be an asynchronous component. So the controller sends a command, but is not able to know if the command is successful or is failed. For this reason, often a sensor is attached to critical actuators in order to provide a feedback to the system related to its operativity or its failures. So we can introduce a wait state in which after having sent a command and set a timer, we wait for a positive event coming from the sensor or a timeout. That means that our command has not been executed. the verification of such a behavior is performed as usual by means of a constraint and pre and post condition, because the wait state is a common state with a constraint that involves a temporal constraint represented by a timer. So the system will wait into wait state, and therefore one of the two states is reached. Another important aspect of this pattern is that it allows us to distinguish the two kinds of behavior. The work state represents the nominal behavior in which the actuator is working correctly, but fail state represents the condition in which the component is failed. So, starting from the fail state, we can implement the fault-tolerant strategies that the application requires. So the two behaviors are formally distinguished and easily identified by this pattern. As I said, part of Statechart can be hierarchically composed, and we are able to identify a structure of the system and to even graphically represent the path of the fault propagation, for example. So from this picture it's visible that, for example, we have rocket A and rocket B. If rocket A fails, it is the engine system that is informed of the failure and then tries with rocket B. If rocket B is not failed, then the fault is contained at this level. If both the two redundant devices fails, then the whole system is affected, then the fault will propagate to the top level. This pattern and the part of Statechart approach allows us to improve modularity, to perform an incremental verification, because the verification of each module is performed in a standalone process, and then to implement a multi-level fault-tolerant strategy, for example. And most important, the communication behavior of the whole system is not spread over all the components, but is contained in the module, in each module. So only important events are propagated along the structure of the system. This is an example coming from a case study proposed by Boreal for nuclear plants. This picture involves a water pump and a pump controller, and bills represent a fault-tolerant module for this case study. With this module, we are able to identify faults of each pump and to implement the multi-level fault-tolerant strategies. Okay, let's now move on to the macro-state constraint management. Like in Statechart, it is possible to embed a state machine into a macro state. But differently from Statechart, we need to deal with the constraint verification. So this is quite explicit. We have an embedded machine into an external state. That means that the external state constraint, C1 for example, must never be violated by the contained state machine. In order to prevent this, we could remove from the internal assembly the components that are involved into the external constraint. This is a rigid approach because the internal state machine will not be able to, let's say, to talk with, for example, the Z component. And it is preferable to perform a verification of the containment of each embedded constraint into the external constraint. For example, C2 and C3 must be contained into C1. And if these properties are verified, then, and if the transition post condition is contained in C2 and C3, then the external constraint will never be violated at runtime. This This macrostates helps us into incremental verify the system, because the verification of the embedded state machine is performed in a separated process with respect to the, let's say, layer 0 state machine. So we have an embedded verification, we can say. Now let's move to the complexity of part-of state chart verification algorithm. This is a sensible argument, because when dealing with the verification of state machine, we have the problem of the state explosion. That means that the larger is the system, the larger is the set of the global configuration that we need to explore. This is, for example, a problem that traditional model checking suffer a lot. So even with the many optimization that the researchers provided to the model checking, it is nowadays not easy to verify very large systems. So before to present the result of the main complex algorithm, I need to present the structure of our constraints. Our constraints are defined by means of a state proposition built over 3 layers. The atomic level is represented by device proposition. It's a proposition referred to exactly one state machine, one component of the assembly. Then we build products that are referred to the entire assembly. So a product will represent exactly one assembly configuration that is also named the global state of the assembly, of course. Then a sum of products is the chosen form for representing our constraint, our state proposition. Therefore, a constraint is defined as a set of global configuration that are accepted from the formula. In addition, we have the any and the non-constraints. Any represents the expression that accepts all the states of a state machine. For example, C1 equal to any, it's a state proposition and an atomic device state proposition that say I accept all possible configuration of C1. The opposite constant is known, that say that no configuration is accepted for C1. Any construct is effective in reducing the size of sum, because if we need to represent the area that covers the gray colored cells, the formula is this, in which we accept for C1 all configuration, all states for the machine C1. If we didn't use any construct, the formula is this. We have 5 products instead of 2. So this is a significant reduction. This reduction is important because in the exit zone algorithm complexity is possible, this is the formula, it's possible to see that the elements that participate to, let's say, originating the computational cost of this algorithm are the transition set of autonomous algorithm, the number of products contained into the constraint, and then the number of M is the number of state machine of the assembly, and S is the mean number of state of the assembly state machines. So this is it's important to observe that this is the worst case cost. So actually the cost is not so big, the exponential, because any and none have been proven to be effective in reducing the cost of this algorithm, because first of all the number of products is reduced, and then if I have an any proposition, its negation that is required for the exit zone determination is simply the known expression. So in one step I can calculate the negation of a state proposition. That is not easy. I performed some experiment that showed the great impact of any, in particular any unknown, in reducing the size of the problem. So this is the, let's say, the very worst case cost of the algorithm. Another verification that is possible to perform by means of an algorithm that I developed is the verification if a constraint is internally connected. For internally connected constraint, I mean that every exit zone of the algorithm is reachable from every configuration contained in the constraint. As before, the constraint is gray colored. The algorithm starts from each exit zone and reverse the calculation of each automatic transition, for example, T1, and it discovers the constraint with a reverse approach. In this case, the constraint is not connected because from 3, the algorithm cannot discover anything that is not already discovered. And this problem is signaled to the user, and the user may decide to ignore the problem or not. This will depend on the single application and on single models. But for example, if we have no exit zone, we can say that from here, this exit zone is not reachable. So it's in charge of the user to determine if this is a problem or not in his application. Okay, in addition, I worked on the development of a software tool that allows to apply the formalism to case study or real application. And currently, it's able to design and validate models to handle and, of course, verify the embedded state machine. An important feature is that it's able to provide a log of the verification process. This may be required when asking for the certification of the controller that has been implemented. So this is a log that certifies the correctness of the system, of the controller. Then it discovers unfeasible and incompatible transition, of course, referred to the state constraints. This tool has been used for the verification of the experiment and of case studies, and in particular of the case study of a dialysis machine that I chose because of the safety critical nature of the treatment. So the patient blood is involved into the process, so it's a quite critical operation. There are several components that is necessary to monitor, both in terms of nominal behavior and in faults, because we deal with blood, but also with heparin that is medicinal, and some vital patient vital parameters. This model has been verified by means of the software tool, and the log is available. This is a view of the layer of the system. This is a 4-level hierarchical system composed by aggregates of device and some sensor that is not aggregated to other device. So we have a top-level control logic that is the only responsible for the start and the stop of the treatment, for example. And we have all the discussed feature of the formalism spread across the 4 layers of the system. This is the degraded functioning mode of the steam boiler case study. I show this because we have to distinguish from fault pumps and working pumps, so there is a lot of temporal constraints, for example, and all fault of the pumps are contained at this level, in this chart. And on the on your right, there are the other functioning modes that can be reached, for example, for an emergency shutdown of the system. I also worked on another project. In particular, this one is, sorry for the solution. It's a simulation that I developed for a company that were working on a self-docking system for offshore boats. I developed this simulation in MATLAB and Simulink environment, and I provided two prototypes of the docking algorithm that is driving the boat by means of the state flow component of Simulink, therefore by means of Statecharts. Okay, now the boat stops. Okay. Not good. Okay. Then, in conclusion, Pattern Statechart have been demonstrated to be effective at decomposing the complex problem, the complexity of problems, to be effective in performing the incremental verification of a system. This is particularly meaningful when dealing with a complex system or simply large system. The single component usability is improved, and they should make possible to perform the verification of very large system. So the question is, why Pattern Statechart, that are a novel proposition of the field or the embedded field, should be adopted for real application? I think that while traditional model checking needs to be executed on an implicit behavior, therefore the behavior needs to be extrapolated from the possible evolution of the system, and then a global analysis of a very large behavior tree is performed. Pattern Statechart, by means of the explicit representation of the behavior and by means of the exit zone algorithm and concept, are able to perform the reachability analysis on the neighborhood of each state. So the size of the problem is also reduced both by all the features presented and by the fact that the reachability analysis is performed on a reduced set of global configurations. So there is a summary. The size of problem is reduced from the point of view of the verification this time. And the verification is performed on explicit behavior. So nothing needs to be reduced. The behavior is explicitly represented by the user. And it's possible to highlight incorrect transition, actions, or constraints of the model directly during design phase. So the testing phase should be reduced both in terms of cost and in time. And all the presented features should be useful at reducing complexity. For example, if we embed a state machine into a macro state, we perform two separated verification processes of the reduced size. So even a simple construct like a macro state should be effective into reducing complexity. Okay, I've concluded. This is the list of my publications. If there is any question, I will be glad to answer.